Now we come to the properties with respect to the position in the periodic table of the different periods. First one we will study is atomic size in picometers. You can see here that scandium, titanium, vanadium, chromium, as we are going from left to right with increase in atomic number, there is a decrease in the atomic size. Atomic size is measured in picometers. But what about these 149 which has decreased so much from 152? That we will study as we do the atomic size property in detail for every period. In case of electronegativity for the 3D series, you will find that the electronegativity goes on increasing and till it reaches at zinc where it has decreased. Now the question will be again, why this anomalous behavior of zinc, which we will again study when we study individually about the electronegativity on the Pauling scale. The first ionization energy in kilojoules per mole, you can see as we go from left to right, from scandium to zinc, then the atomic number increases, but the outermost electron is added to the same orbit or the orbital, and it is the 3D orbital. And so what happens, that you know from your previous knowledge that for the ionization energy, the first ionization energy will be the amount of energy required to remove the outermost electron which is loosely held. Here it is of course the 4s electron which is the outermost electron, and we can see here that as the atomic size goes on decreasing, the ionization potential goes on increasing, which is much in accordance with the properties of the atoms in the periodic table. Next we will see that are all the 3D elements called as transition elements? No. Then what is a transition element? Any of the d block elements which has a partially filled d subshell in its ground state or a partially filled d subshell in the most common oxidation state is called a transition element. In the 3D series of the d block, then zinc should not be considered as a transition metal or a transition element because it has got completely filled d orbitals, but it shows many properties very similar to those of transition metals, and so it is placed in the d block and also considered as a transition metal as far as the properties are concerned, only some. Now some of the properties of transition elements are like this. The transition elements are essentially d block, first thing. Second, they have an electronic configuration of the valence shell as n-1d, 1 to 9 and ns 1 to 2. They all have incomplete d subshell in their valence shell in the ground state or in the most common oxidation state of the ionic state. They show variable oxidation states from 0 as a least in pure form to a maximum of +8 as in osmium tetroxide. Now all transition elements will show complex compounds. Exception is scandium in +3 and zinc in +2 oxidation states. Scandium in +3 and zinc in +2 oxidation states do not form colored complexes, as scandium has got no empty d orbital then, and dd transition is not possible. Scandium has got in fact all empty d orbitals, and the dd transitions are not possible because when scandium is having outermost shell configuration as 3d1 4s2, in the +3 state all the 3 electrons are lost, and so the d orbitals become empty. So there are no electrons to jump in the d subshells, and therefore no dd transition. So no absorption of energy from the visible region. Now therefore scandium 3 plus complexes are colorless. While case of zinc has got completely filled d orbitals. Zinc is most stable in the +2 oxidation state where it has lost the 4s2 electrons, and therefore none of the unpaired electrons are there in the d subshell. They are all paired, and if there are no unpaired electrons, there will be no jumping by excitation of absorption of visible region radiations. Here you can see the colors of the complexes. CrH2O6, it's a complex which we write in brackets, and the ligands we write in small brackets. Here it is FeH2O6, which is pale greenish in color. Then you can see the cobalt complex, the nickel complex, copper complexes, and again there are other complexes also of cobalt, that is cobalt tetrachloride, which is bluish in color. We will learn about these color variations for the different ions of the D block. Now here you can see that once the light which is absorbed is of a particular wavelength, then the color that you will see will be a different one. So if violet is absorbed, you will see a green yellow color. Violet light is in the range of 400 to 435 nanometers. Similarly, if blue is absorbed, you see the yellow color of the complex. When you see an orange color complex, you will be sure that it is green blue color in the range of 480 to 490 nanometers, which is observed. Again, when the blue green color, here 490 to 500, it is the cyan color, and you get the red color complex. So if you absorb the wavelengths which are shown in the left hand side, then the corresponding colors of the complex that you will see will be for the as it is written in the right hand side. So a green color complex means that complex had absorbed a visible region wavelength from 650 to 750 nanometers. The green blue was 480 to 490 nanometers, but the blue green is from 490 to 500 nanometers. So when you see a blue color complex, as you see in blue copper sulfate solution, then you will know that the complex had absorbed 580 to 595 nanometers of light of the visible region, that is the yellow color radiations. Now what makes the complexes or compounds of transition elements colored? So whether they absorb, and why should they absorb? Because when a complex metal ion or a metal atom is being approached by ligands. What are ligands? They are atoms or groups of atoms which can bond with the central metal atom and form a complex. The central metal atom is obviously the atom of the transition element. So when these metal atoms are approached by ligand atoms to form a bond, then they cause, who is this they? The ligand atoms or the ligand molecules, they cause the d orbitals of the central metal atom to split. Originally they were degenerate, that is of the same energy. Now after the bonding of the ligand atoms, they have split into different types of orbital sets, dxy, dxz and dyz, and here we have dz square and the dx square minus y square, which have gone above, which have got an increased level of energy, while the dxy, the dxz and the dyz have got decreased energy. Further, they can be further split, as you can see here, the dz square, the dxy, the topmost one is dx square minus y square. How and why these take place, we will learn when we learn about complex compounds or complexes in details. Now, so we can say the reasons for the transition elements of the D block showing colored complexes are: first, unpaired electrons; second, DD transitions; and